Good afternoon. So today we'll discuss a little bit more extension on X-ray diffraction technique that will focus on single crystal XRD, grazing angle XRD, synchrotron XRD, and X-ray absorption spectroscopy. If time permits, we will discuss neutron diffraction. So as I discussed in last class, X-ray diffraction techniques mainly, I've discussed in last class about powder XRD. So that powder XRD mostly gives you crystal structure. It's it's a crystallite size. How that this lattice parameter as well as this strain, stretch, those things can be found out. Those we have discussed. So today we will first discuss about single crystal XRD. Okay, first coming into single crystal XRD, if you see in single crystal XRD, it's mainly use a rotating crystal methods. That means you have see this sample is mounted on a soft holder like this, and in rotating single crystal method, a single crystal is mounted with an axis normal to the monochromatic light. You can see you have an incident X-ray source is coming from this incident beam, and you have a crystal that single crystal mounted on a rotating film. So here, after once it's passing through this, you will get a reflected that being the cylindrical on the film, you will get a signal interference that you can spot it out here. So as the crystal rotates here, since in case of powder XRD, you have theta 2 theta you are varying by the source as well as theta 2 theta as well as theta variable instrument are available where that source and detector angles were changing. But here the crystal is rotating. So since crystal is rotating, a set of lattice will some point make a correct Bragg's diffraction angle, and the diffraction will form. So the crystal is keep on rotating. So X-ray beam is falling. So when a set of plane that will make right Bragg's angle with that of incident beam, will able to see a diffraction. So by recording the diffraction pattern, both angle as well as intensity in various crystal orientation, that since particularly that crystal is moving, rotating, so you have a various crystal orientation. So you'll able to get the shape, size, unit cell as well as atomic arrangement. That means you will able to get bond length, bond angle, site ordering, everything you will get, which this bond angle, bond length that we are not able to get in case of powder XRD. Those things you can be able to get here. And single crystal XRD allows the absolute structure determination, like you can identify an unknown crystal through single crystal XRD. So with specialized chamber, like you can do high pressure or high temperature, experiments you can do. You can identify the form that different phase formed during a heat treatment, during a pressure treatment by the single crystal, XRD. So if you see a rotating crystal method in there, the mostly 3 to 4 cycle goniometer is there. That means that cycle refers to 4 cycle, that you have a 2 theta variation here. You can see incident beam is falling here. Your crystal is here. That crystal is rotating. So that crystal is rotating at phi, and then you have a beam direction is this, and your detector is here. So you have a 2 theta variation here. So you have a 2 theta variable here. Then theta orientation, phi orientation of the crystals. Then you have another 2. There is a stage rotation. That is omega, and in addition to that, you have a phi rotation with respect to the beam stub, that is chi here. So you have a 3 to 4 goniometer here, and this circle refers to 4 angle that determines the relationship between the crystal lattice incident ray and the detected crystal position. And then you have a incident ray then the rotation of that crystal and beam direction on that basis. So samples are mounted on the thin glass fiber using, mostly we use a epoxy type or a cement. That sample will be mounted on this, which are attached to a brass pin is here, and then we mount into a goniometer. So both X, Y, and Z direction can be orthogonal and allows centering to the sample has to be the center of these three to the X-ray with respect to the X-ray beam. So the beam stop is located at the just behind, the opposite to the colligometer to plug direct transmitted ray. So because that may be burn out your detector. So that beam stop will not allow the direct beam. So whatever the diffracted beam, that will go to the detector. Okay, so then if you see in the single crystal XRD, mostly the detector we use, the detector is a charge coupled detector, mostly a plate detector or a 2D detector. We can use a charge coupled detector nowadays. So modern single crystal XRD uses charge coupled detector that transform X-ray photons into an electrical signal, so that whatever the X-ray coming here, so after diffracting go to the diffraction pattern here, and then that will be transformed to converted to electrical signal, which then process to a computer processing systems. So diffraction pattern at each angle can be used to produce a 3D density map. You can see here. So after the diffraction pattern you spot, you get, so that what can be Fourier transform, and then you will get the electron density depending upon the element. You will say electron density mapping. So based on the electron density mapping, you can create a 3D structure, whether it corresponds to oxygen, carbon, or nitrogen, and you can, based on atomic model, you can find out the crystal structure. But we have some limitation in single crystal XRD. First thing, you must have a single, crystal. That is a polycrystal system or a polycrystal material you can't use in a single crystal analysis. You need to have a single crystal that stable samples, and generally between 50 to 250 micron size. And that sample has to be optically clear. That means that X-ray beam should be transparent. That means optically transparent sample is necessary. A twin sample, that if you have a twin or some rough surface, so that is quite difficulty to handle, because that difficulty mainly arises because of the X-ray beam has to be centered with respect to theta, to omega, phi, and psi variation. So that is quite difficult if a twin sample. And here the data collection takes quite long time, that is 24 to 72 hours, whereas in case of powder XRD, we take in 2 to 3 minutes, we're able to get a very good diffraction pattern. But here you need to go for a long run scan. Then after, once you got the crystal pattern, and then you will be able to refine using various software like CellX, OLX2 software. So those type of software you can use, like powder XRD. You can use various software here to identify that structure. So as you know, the single crystal XRD was helped to identify a structure of DNA. So that Watson and Crick, they got the Nobel Prize because of this DNA structure analysis. That for that analysis they use this single crystal XRD. So if you see the history of single crystal XRD, Rosalind Franklin, physical chemist and crystallographer, who first discovered that, bound B DNA that he discovered, and then Watson Crick combinedly, the information on photo 51, this is a photo 51 film, from the photo 51 film, by using molecular modeling, so they are able to solve the structure. You can see here, so there is a X type of pattern in this film. You can see, so you can see there is a X type of, you can see the pattern is here, X pattern. That X is remaining a helix structure. Like if you see DNA, you have a double helix structure. So that X pattern here in this figure is a, the double helix structure. And then you have a 4, diamond-like structure. 4 diamonds, that's mainly extended, molecules. Like that DNA structure is quite extended, long chain. So that because of that long chain, you are getting 4 diamond rings. And then you can see that shimmers lines are, you can see here some blue lines are here. So these blue lines reveal the distance between repeating structure. In DNA, you have a CTAG, like cytosine, guanine, adenine, tyrosine, like CT, that those type of sugar molecules. So they are arranged in a proper fashion. So those distance between the repeating structure, so that you are getting here this type of lining. And then if you see in the line, there is two missing line was there here, this one here and here there is a missing line. So that indicates that interference second helix, because since there is a one helix is here and another helix is there, DNA double helix structure. So this red line was missing because of the interference. So by getting this information about the helix structure, then long chain, then you have a repeating structure and double helix structure. With that information, you get double helix. This which is respect to that other parameter they obtained from combining a DNA made up of sugar, phosphate, nucleotides, CGT, as well as percentage. By combining those things model, so they established this DNA crystal structure. So that was the best example, first discovered DNA structure by using this single crystal XRD. You have a complex structure like C32, H36, Cl2, PT. This is a platinum tellurium chloride complex, which is monoclinic structure. So using that the single crystal X-ray diffraction pattern, by identifying the position of all the carbons, and then that whatever the platinum, and here is the platinum, and then the chlorine and tellurium atom, by calculating the electron density and angle and the bond length, you can able to predict this crystal structure using single crystal XRD. So I have just, it's like that. I have just discussed about some glimpse of about single crystal XRD. So you can go and read more detail about the single crystal XRD to how you can interpret those data. So mostly, if you see the single crystal XRD, those will be useful for analyzing a single crystals, and that from that you can predict the crystal's electronic structure by using various software. And finally, the unknown compound can be identified, its bond length, bond angle, those information you can able to get using single crystal XRD. So another XRD technique that we will discuss now is for thin film. Like if you have a thin film, so it's difficult to use, single crystal, as well as, this much information you cannot able to get using powder X-ray diffraction technique. So for that case, you have to go a grazing angle XRD, or you can say thin film XRD, or grazing angle, or glancing angle XRD. So where theta is very, very low, 1 to 10 degree, in that region, you have to find out here. You can see here, you have a substrate here, the green one, this is the substrate. On that substrate, you have a thin film coating or a thin film of any material here. So here you can see in common X-ray XRD, your angle is quite large. But here in a glassing angle XRD, we are taking angle is very, very small. So theta is less than 5 degree. So that X-ray is focused. If you see here that it will take high angle, your penetration interaction here is quite low. If you take a grazing angle, you can see here that your penetration, you can go up to this. So you have a higher interaction volume here. So that here is because of that is mainly the top structure you want to focus. If you go like this, X-ray may penetrate into the substrate. That has common. If you take conventional XRD, the X-ray can go inside and it can touch the substrate. Then in the pattern you will get the substrate effects. So the peaks from the substrate. But since we want to only focus on this top surface, you can take a very low angle where X-ray will be penetrate only up to the certain extent in the lies in the thin film area. So grazing angle XRD can be performed. Many analyses possible with powder X-ray diffraction with added ability to provide information about depth profiling by collecting successive diffraction pattern. By changing the angle, you can your depth can be changes from 5 degree to or 1 degree to 5 degree or more. If you go, your angle of incident will change. So because of that, your penetration depth will be changed. So based on that, you can able to find out different, depth profiling when able to find out, orientation of thin film with respect to the substrates, lattice mismatch, that you have a substrate and a film on that surface, how the lattice mismatch happening between the top interface of these, that is the interface characteristic you are able to find out, and epitaxial or structure growth, or whatever, how the strain is built up because of that thin film deposition on the substrate, and those information you can calculate, find out by using even X-ray reflectivity. You sometimes at gauging incidence, X-ray reflectivity measure that thickness, roughness, density of the film. Those things can be measured. But here this technique does not require a crystalline film. It works even in amorphous material. You can able to get information about the surface depth profiling by using gauging angle XRD. You can see here how your theta, that you can see the in gauging angle X scan, omega is fixed at an gauging angle while 2 theta is scanned. You can see you have a incident angle here is fixed at omega, and then 2 theta is changing here to find out a different information. So the tags here will be, our challenges are weak signal to ultra thin film. Like we can see here in this is a thin film. On this thin film, you can see here this is a plane, particular plane. That plane is normal to the diffraction pattern. Here diffraction normal to the diffracting plane. Then the diffraction is coming from this plane. Then once it's rotated, so another plane will come into the picture to this. So you'll able to get another peak. So if you the angle of incident that you will change, or you can simply change the detector position, you can able to see the other plane also. By changing, you have a incident angle is fixed at omega, but 2 theta is changing here. Here you can see here, and this here. So by changing the 2 theta angle, you can able to get different fix you will able to get. So weak signal from ultra thin film. It's a very thin film. Sometimes the signal is very weak. In that case, so you can glancing angle XRD geometry increases, layer signal by increasing geometry, by changing the geometry of the sample, and by changing the this 2 theta position, you are able to get better signal. So overlapping of peaks, so that GIAD helps distinguish. Like in polycrystalline material, there is a possibility that you will not able to that overlapping of peak, but here you once crystal oriented according to the incident ray, you will able to that overlapping of peak can be overcome. And what are the stress strain measurement that can be possible by using the depth profiling analysis, and phase identification can also be done. And dealing with texture sample, as I told this example, once if you have a proper orientation, and depending upon the size, shape, or unit cell parameter, you can able to get all those information by changing the detector to incident angle here. So then if you see instrumentation part, you have a some X-ray source here, and that is falling on a global mirror. From there it will go to the sample surface. You can see here the angle of incidence is very low, and then here the sample diffraction, the normal vector is this one, and diffraction wave vector that is here. And by rotating the sample rotation, that 2 theta variable position can be changed, and it will fall onto the monochromator. From there it will go to the detector. Like from the source it's going to the sample, then to the flat monochromator, then going to the detector. So this is if you see the instrumentation part, it's almost similar to that of normal powder XRD pattern. Only difference is that the angle of incident is very low in this case. So you can see this is an example of that this TiO2 photocatalyst on a film substrate. You can see if you this theta to theta coupled scan, that is a normal XRD, conventional XRD scan. Here in top one is on a gauging angle incidence 2 theta scan. You can see the unattached peak, that those unattached peak you can able to see very quite intense in case of gauging angle XRD. Then from the conventional, these peaks you can see almost missing here. So those information are able to get by whether your phase is formed or not using gauging angle XRD. Similarly, you can see this is an example of a solar cell. You can see how the varying that omega, that 0.51, and that those things by varying this incident angle, you can able to all those parameters peaks which are not observed in case of normal X-ray. So those things you can able to see all those intense peak or that you can be able to see. So in normal XRD, a large portion of diffractogram comes from the substrate. If you take a substrate, thin film substrate with normal XRD, what will happen? That whatever the peak information you will get, so those is mainly that you will be able to get from, because of the high penetration of the X-ray, you will be able to get from the bottom surface, that is from the substrate. But if you go grazing angle XRD, it will change it from like this, you change like this angle, then what will happen is mostly lies on the thin film area. So that because of this, the peak diffraction, peak intensity will be enhanced. So one of the best example, if you take a solar cell that is made up of molybdenum substrate on CIGS and top zinc oxide substrate, you can see when you have a grazing angle here, you can see on this omega is 0.45. Here you can see the peaks is mainly from the top surface, that Zeno peak you are able to see here in the top surface. But when you go the omega equal to 1, you see that X-ray beam is going into CIGS layer, your additional peaks you are able to getting from because of that CIGS signal, that is solar cell. And then if you change the angle higher, that omega is to 2 degree, you can see when touching to the molybdenum side, so you'll be able to get the peak from the molybdenum. So based on that, you can depth profiling is possible by varying the incident angle in grazing angle XRD pattern, and you can identify whether you have formed a perfect structure or not. So you can see here a substrate that tungsten TWC on that titanium nitride, titanium carbide, and titanium nitride again was deposited. And this is the interface that TIN and TIC, the yellow, then this cyan color, you can see intermediate in between these two zones, you have a variation of this structure, this, that intermetallic structure is here. So that is mainly TICN. TIC is the bottom layer and TIN is the top layer, and in between there can be growth intermetallic TICN. So those information you can able to get from depth profile. You can see here that initially you have a 2 degree like here. By changing the depth, you can see here this is the main peak is here due to TIN. But when you go keep on interface, you can see that TICN peak is developing at higher angle, that once the degree is higher, that penetration, like initially your first penetration X-ray is going this, and then if you go slightly till, it will go like this. You can get to interface, the interface you will able to get here, then it can go inside, so you'll get this is the TIC peak now developing when you touch upon here. So best like that, you can do depth profiling, and you can see when you can measure the stress and orientation of the structure. You can see because of this is the structure on stress sample. If you elongated stress, like tensile stress you applied, so what is happening, the lattice plane is now stretched. Because of that, you can see the peak is from black to yellow, the peak is getting shifted because of the residual stress. So those information, the shifting of the peak, that you can able to see by using this residual stress, that you can find out. So this is a bismuth titanate on strontium titanate substrate. You can see the 004, 006, 008, 10, 12, 14, 16, all are higher order peaks of 004. So there it shows they are oriented in particular direction, 004 direction. So all those orientation information you can able to get by using grazing angle XRD because of that layer structure. So you will able to get this particular oriented structure using this X-ray in this thin film XRD. So from thin film XRD, mainly we will able to get information about the intermetallic structure between two layers, as well as top layer and bottom layer. Mainly on the thin film substrate you can able to get, and then you can use them to get information about stress or strain built up in the material, or as well as by using depth profile you can able to find out the composition or the variation of the element across the interface. So, so far what I discussed, that X-ray source is mainly a conventional X-ray source, that is mostly use a tungsten filament, and the tungsten filament that lies yes, because of thermonic emission, the electron generated, those electrons fall on the copper target or molybdenum target. From there, you will able to get the this X-ray generation, that is with copper K alpha or copper K beta or L gamma, whatever you'll able to get from there. But so in this case, the most drawback is that your detection limit is point it's much above that 2% doping element should be there, and then your in terms to the intensity or brightness that a conventional X-ray source is not that strong. So to get more information, like you can very low concentration of doping element is there to identify those things, or even a less time fraction to get better result, we can go for synchrotron X-ray diffraction pattern. So here synchrotron source are used as a X-ray source here. So if you see synchrotron XRD, that in synchrotron XRD, that you see, first of all, it has a synchrotron, that means a ring, this type of ring is there. So this type of ring is there. But synchrotron is a ring which uses magnets. You can see these are the magnets here. So various magnets are placed here, and magnets and electrodes to accelerate the X-ray or light nearly to the speed of light. Like when the X-ray is passing inside this synchrotron, it keep on circulating. So because of that, it will attain a speed, the accelerate up to a speed of light. So the speed is very, very high. Then synchrotron, then what will happen? The synchrotron radiation is an advanced collimated light source. So because of high speed, particularly these are the different type of outlet that from where that you will able to collect that the data. So you can see the outputs here. You will able to see. So at different equipment you can get out of the data, and then that X-ray source, high speed X-ray, highly energetic. Those things you will get, and then you can go for the analysis. So synchrotron XRD produce X-rays that are monochromatic, like earlier case in conventional K alpha and K alpha 1, K alpha 2, you have a splitting over there. But here, because of highly monochromatic, so those things can be neglected. It's right energy for detection of even carbon and hydrogen can be detected by using synchrotron XRD. In addition, no conventional diffraction pattern, it enables pair distribution function, like how that in an amorphous material or a diffuse scattering, how the different atoms are arranged by using atomic pair distribution function. We are able to get those information by enabling to find. This will help you to find bond length, coordination number, even those are not fully crystalline. And it has many advantages over structural characterization of material at atomic or molecular level. And even you can use these even at stress element analysis by using synchrotron XRD. Because the synchrotron XRD has peculiar properties that have some advanced properties, so that enhances the the XRD pattern. The more information we are able to get. For the first thing is high brightness. The brilliance that the X-ray that produced in third generation is about 10 to the power 5 to 10 to the power 12 order, whereas in case of the synchrotron radiation, it is an order of 10 to the power 23. So it's highly monochromatic and highly collimated. Like synchrotron light parallel, therefore the speed spreads minimally through the propagates. So that is highly collimated. It's a wide energy spectrum. So radiation, it can include wide range from infrared to hard X-ray. So depending upon your usage, you can choose the particular wavelength, and then you can go for the determination of the X-ray diffraction pattern. It's a short pulse time structure, like pulse level is very, very short, so better resolution at the same time scale you can able to get, and it has a high penetration because of high brightness, the penetration is depth is high, so it can be able to do in a time result or high resolution in situ experiment can be possible. In a fraction of second you can able to get better information. So if you see the optics of the synchrotron XRD, we have a synchrotron source here. Then because of the electron is circulating here, it will come out, and then it will fuel on the mirror. It finally goes to the single crystal focusing crystal structure, and then it will go to the focusing mirror and finally slits, and it fall in the sample. So before coming to the sample, that X-ray source has to be going through different space to enhance that this brightness and all those things, you'll be able to get highly intense X-ray beam that will form the sample, and you will get the better XRD pattern. So here, that whatever the beam lines, that means that synchrotron XRD beam line refers to instrumentation that carries synchrotron beam to the experimental end station. So this whole thing will be the beam line structure. The X-ray will be generated here. Electron from then, once generated, go to the sample, so you'll be able to get whole structure. And it can be used many various focusing mirror and those things to highly this collimated, to produce collimated beam. So if you see the optics of a small angle XRD, so because of the monochromatic with high flux and highly collimated beams, since that highly collimated, so no K alpha 2 diffraction peaks you will be able to get in here in smooth XRD, and you have a high signal to noise ratio as well as high angular resolution you will be able to get, and you can even analyze complex structure, the refinement, by using the X-ray produced by single proton X-ray source. When combined, this is a single crystal synchrotron XRD can combine with different ultra fast or steady state techniques, solid state detectors, different techniques where you can detection limit can go to 0.18%, which was about 2% in case of conventional XRD. So it is much high sensitivity, and samples should be finely and uniformly bound to the particle the size of less than 20 micron and loaded into the gas capillary that there. So you can see here the sample will be glass capillary source which will be generated here, and then you will be able to get proper XRD pattern. You can see this is a XRD pattern of a coal fly ash. You can see here that there are some this L XRD that is normally available, the conventional XRD, laboratory XRD, and this is single synchrotron XRD, black one. You can see there are some of the black one. These are the peaks. So these are the peaks that the intensity. You can see how the additional peaks can be observed in case of better using single synchrotron XRD, even at very low concentration of impurity that can be identified using this type of pattern, this type of XRD. So if you see here in synchrotron XRD, you can also use this facility for high temperature XRD measurement as well as high pressure. If you see the synchrotron temperature dependent spectra here, you can see that how that particularly 100 peak is changing with the temperature from 300K to 613K. So that shifting here like this in this direction. So that is clearly showing that there is some sort of doping is going on. So those type of because of change in the temperature effect. So that here in this particular example, that lead, lanthanum, titanium, aluminate, the tetragonal to cubic phase transformation, that thing you can able to see by using this type of synchrotron XRD. Similarly, high pressure also you can see here, depending upon the pressure, how the peak is shifting there. So the high pressure experiments you can do in hexagonal here, mainly hexagonal structure gradually shift to peak to a larger angle with increasing pressure. So because when the pressure is increasing, that this peak position is changing to higher angle. So those information you can able to get using this type of synchrotron XRD. So that synchrotron XRD, if you see that it combines with, you can combine different techniques with synchrotron XRD, then it is possible to find out better information. Like you can combine the Raman spectroscopy, X-ray absorption fine structure spectroscopy with this synchrotron XRD, you can able to get better information. The mapping of chemical, physical, and crystallographic properties of the sample in 2D, 3D using smart combination of diffraction, imaging. Like you can integrate different techniques, diffraction technique, imaging technique, and spectroscopy combined together to get better information with a synchrotron X-ray source. For instance, if you take energy dispersive time result, JAX X-ray absorption fine structure, and XRD combined, you'll be able to see how thermal evolution occurs in magnesium hydride niobium oxide mixture. So if you have two-phasic system, then you can able to see what is the phenomena is happening, or what are the new things that are appearing, so that phase growth that can be identified using this. So from this one will discuss that X-ray absorption spectroscopy, how X-ray absorption spectroscopy, that's mainly two types. One is X-ray absorption, near edge spectroscopy, and extended X-ray absorption, fine structure. You can exhaust or exness that commonly combined with this synchrotron radiation. Using high energy X-ray, you get more precisely data. Like better information you can able to get by using this type of technique, that X-ray absorption technique, in addition to this X-ray, this synchrotron XRD technique. So we will discuss about X-ray absorption technique, that's X-ray fine structure spectroscopy. So that mostly divided into two X-ray, that's one is X-ray absorption near edge spectroscopy, another is X-ray absorption extended X-ray fine absorption spectroscopy. So if you see that X-ray absorption spectroscopy, that here the intensity of an X-ray beam passing through a material, like you have a material, it's like this. On the material, you are passing the X-ray beams. So what happens? So because of this X-ray beam, it can be attenuated inside the material. So whatever the intensity, that absorption coefficient depends upon the intensity that you will able to get. That is mainly on absorption coefficient, I equal to I0 into e to the power minus mu x. So that mu is absorption coefficient, or you can express mu by rho, mass absorption coefficient. And this mu mainly depends upon the energy of the X-ray, what is the energy of the X-ray that's falling on the material, and atomic number of the material, as well as density and atomic mass. So mu is proportional to rho into z to the power 4 by a to the power 3. So this depends, it's both this material as well as X-ray source, which dependent on both the things, and then X-ray absorbed through the process of the whole absorption spectroscopy based on photoelectric effect that we discussed. That when you have a 4 electron, that X-ray beam will come here, and then it can be throw out this electron out here. Then you will able to get a vacant orbital in this case. So that photoelectric effect that we discussed, that is X-ray absorption technique, mainly depends on that. So if you see, the absorption occurs when an incident X-ray are energetically enough to remove a core level electron. That means as you discuss in photoelectron spectroscopy, that h nu, that the energy of the X-ray, incident X-ray, should be sufficient enough to overcome that binding energy of that particular core level electron, and then once it overcome that core level electron, that inside that electron will remove from the core, so that will be escape as a photoelectron. So this absorption process occurs when excitant X-ray are energetically enough to remove that core electrons. So the excitation of the core electron, like you have a core electron here, and because the sufficient X-ray energy is falling here, so because of that, this electron will migrate to the unoccupied state, not to the vacuum, just lies in the unoccupied state. So this excitation of core electron to the higher unoccupied state, that is or below, just below the continuum, it will be excited to that layer. So extremely sensitive, like this electron was bound to that atom, and it's quite close to the nucleus. So this extremely sensitivity to the chemical state and local environment of that particular electron, because it's close to the core electron, is close to the nucleus. That bears more information. You can see here KLM cell based on Bohr model, and then when you have a K electron, K2, this 1s2 H transition, KL, L1, L2, L3 transition, depending upon that, you can name it different H transition. That means when there was that atom was there lying inside, that particular electron was there in the material. When X-ray falls with sufficient energy, that core electrons knock out, and till that, what will happen? The absorption will be slightly less. Once that you overcome that energy barrier, that binding energy barrier, then what will happen? So suddenly there is a bandage. Increase will be possible, so that you can see here. So once you have a K alpha, so there is a sudden change here, and then if L case, so there is a sudden change. So because of this absorption, and the absorption shifts occur, that when necessary energy or the binding energy of a core electron transition is attained, that particular binding energy is attained, the mass absorption coefficient, that mu, that whatever the absorption coefficient mu was there initially, once it reaches the binding energy level, that mu is drastically changed, and because of that you will get a absorption peak here, absorption edge, this type of absorption edge you will able to see. And this each absorption edge is characteristic of a particular absorption wavelength. So that means its technique is specific to the each element. So its X-ray absorption technique is specific to the its individual element. So it gives information about bond length, bond strength, nearest neighbor atom, and defects. These are those things you are able to find out. Like if you want to see there is a core electron, how many electrons are surrounding to each other on the same 2D structure or same in a 3D structure, like you are able to say the near atom, near neighbor information, and how they are sharing whether 12 coordination, 6 coordination, 4 coordination. So those information you can able to get from X-ray absorption spectroscopy. So that each edges are labeled according to the cell where the core electron originate, whether it's originating from L cell, you can term it as L, your K cell, you will term it as a KH structure. So each edge you can see that K edge of iron, nickel, copper, molybdenum, they're quite different to each other. Similarly, L edge they are quite different. So these are critical absorption wavelength to a particular element. So that's why X-ray analysis is you'll get specific technique. So we'll take 3-minute break here. Then we'll discuss about two parts, that X-ray absorption spectroscopy, that X-ray absorption fine structure, that how that near edge as well as fine structure. So those things we'll discuss after short break. So we will now discuss about X-ray absorption fine structures spectroscopy. So that absorbs that is a part of X-ray absorption spectroscopy. So like you have a bandage, the particular once you have attained a particular binding energy. That because of that, once you reach the binding energy, that H nu is equivalent to binding energy. What will happen that core electron will knock out, and because of that, once it's knock out, that nu, that attenuation coefficient, absorption coefficient will sharply changes, and you will get a sharp edge peak, band edge peak. And we will now see that this the near and above that how the band structure, because of that peak, the near edge and band edge absorption structure changes with respect to the this X-ray absorption fine structure that we will discuss. So if a core electron that propagates, as you know, this is a core electron, so that electron in a spherical wave function, it will propagate like this, and like this, like spherical waves, it will go on that spherical wave, it will go like this. So core electron propagates outwards. One, it will generated from here, and then it propagated out in all the three coordinates. So it will be a spherical wave. So where it follows, with de Broglie equation that lambda equal to h by p. So as you know, this whole thing that this X-ray absorption fine structure spectroscopy is an interference effect. Like how whether like one electron is here, another electron is here, and another electron, like these different electrons are here. So X-ray is coming and falling on this. So what will happen? The wave proper pattern generated from one electron will be interfere with the another electron. So another electron is generating here, like this electron is going like this, and this electron is going like this one. So because of that, there will be interference between two wave fronts. So mainly since this is a depends on wave nature of that photoelectron, it's convenient to think that whole X-ray absorption fine structure spectroscopy in terms of wave vector, the wave number rather than energy. So we'll express that energy in terms of K here. So if you see kinetic energy Ek equal to half mv square, so that you can write using these two equations, K equal to 2 pi by lambda. So you can, that is p square by 2m, then that p you can value, you will get h by 2 pi k square by 2m here. So then your Ek is kinetic energy, that will be difference between h, this h nu, that is the he, that's the h nu, that X-ray photon, minus that binding energy, that h nu minus E0 here. So you can express here K equal to square root of 2 pi by h whole square 2m by h nu minus E0. This h nu is nothing but E, that is wave vector, that is the X-ray, that photon energy you are applying, and then you can see here all those parameters are constant. So it will be only K is only varies with respect to E minus E0 or E h nu minus E0 here. So this is the only variable term in case of X-ray fine structure, and that is this one. This is the h nu minus E minus h nu minus E0 is the only variable. Like as you know that you have a core level electron here, and we are applying X-ray. That X-ray energy is now insufficient, like low energy, not enough energy is there, not enough energy. It's that whatever that this electron, this knockout electron will not go to the continuum. Instead of going to the continuum or outer space, it will lie somewhere in the unoccupied valency states. So there you will say low energy exness X-ray absorption near end structure you will able to see. But if your energy is sufficient to knock out that electron from the core level to the outer layer of the optimum, the unbound structure, that this is the continuum structure, just enough, just enough, then able to escape into the continuum. So this electron will come out to the continuum, and while it's coming out, it can interact with all the neighboring atoms. It will interact. So because of this, you have a multiple interaction, like this electron interact with this. There is a possibility of multiple scattering here in case of this exness that will give X-ray absorption near edge spectroscopy. But if you energy is sufficiently high, that means that is quite high energy. If you apply very high Ek, and that will happen. So backscattering, that wave pattern of this, instead of interacting the wave pattern of this, so it will directly go into the continuum. So here that you will see the X-ray absorption, extended X-ray absorption fine structure you will able to get. One is near edge, and one is extended edge structure you will able to get depending upon the what is the energy you are applying on the material. So if you see that X-ray absorption fine structure of a free electron, you have a core electron here, that is the observing atom, that X-ray is falling on this. So because of this X-ray falling on this, once that binding energy reaches to this electron will knock out from this to a continuum. So because of this, what will happen, you will be able to see the a wave pattern is generating in this system. So here, so K in that equation will able to this wave pattern generation. So atom absorb the X-ray energy E and destroying the core electron of energy E0 and creating a photoelectron of energy E minus E0. So it has a wave pattern, so it will destroy that wave pattern and that new photoelectron will generate with creating a photoelectron of E minus E0. So that photoelectron, that wave vector will propagate like this. Because of these changes, what you will see, the absorption coefficient, you will plot energy versus H. So you can see, you will see there is a sharp absorption. So this change in absorption is mainly possible with respect to this, once the binding energy K, binding energy attenuated and K is changes. So once E is large enough to promote the core electron to the continuum, so there is a sharp increase in absorption spectra you are able to see. So this is only in case of a free electron, free atom. So that the isolated atom, if it is a mu E, the mu E has mu E, the sharp step, the core binding energy and is smooth Fe. That like means you can express it a mu E, that the energy change here function that into the function of energy that you can able to change here. So if you see the interference of neighboring atom, that there is in previous case I was discussing only single atom, but if you have a scattering atom is there, like one you're observing atom at core level, and there is another atom, just scattering atom. You have a blue here and you have a red here. The blue is your observing atom and this is red is your scattering atom. What will happen? The wave vector K generated from atom blue will be interfere with the wave vector from the atom from the red atom. So because of that, with another atom nearby, the ejected photoelectron can scatter from the neighboring atom. So this one will be scattered from the neighboring atom. So you will see one blue wave vector generated from this, and then they will be scattering from this. So because of that, you will see a interference. The backscattered of photoelectron will interfere with itself, and because of that, you will see the amplitude of the backscattered photon at the observing atom will vary with energy E, causing a oscillation in the absorption bandage. In previous case, which you see, there is a sharp change you will see like this instead of this. So in the other case, when you are neighboring atom, you are seeing a interference like this that is producing here. You can see there is there is only single observing atom, blue one. You can see the sharp line you are able to see. But in case of red atom is there, you can see that red line here. That is because of the interference of these two. So EXAFS is an interference effect of photoelectrons with itself due to the presence of neighboring atom. So that neighboring atom is there. So that because of that neighboring atom, that electron wave which is going from the observer, it will be scattered back from the scattering atom and it will interfere with each other. You'll be able to see a wave pattern in that. So mainly if you see that in this X-ray fine structures phenomena, in that spectroscopy, two parts are there. One is this exynase and one other is EXAFS. That is before that absorption, you can see absorption coefficient of energy. Here absorption is low. Once that band edge appear, so you have a absorption here. So this absorption information you will get and the absorption here. Then once the absorption is attained here, then because of the neighboring atom, you will see the wave pattern here. That is because of extended X-ray absorption fine structure spectroscopy will get from this zone where this band edge, near the band edge, you will able to get X-ray absorption near band edge emission spectroscopy. And you will also, that pre-band edge here, some information you will able to get from here, but mostly the two information that you will get, one is from exynase and EXAFS. The shape of the edge of the pre-edge resonance are characteristic of the local symmetry of atom. So whatever the shape you will get here, so that shape will depend upon how the local symmetry, how the atoms are arranged in that systems. So they can be used as a fingerprint to identification of local structure to get the information about bond structure, the bond length, coordination number, neighboring atom, all those information you will able to get. So analysis of photoelectron scattering by surrounding atoms near and above each core level, the short range interaction. From that interaction, you are able to interpret the data. And X-ray absorption pre-edge region extended this X-ray absorption. This is up to few electron volt only. And then beyond that, you will get this X-ray absorption fine structure, and this region, it's very sensitivity, like if it's chromium +3 state or chromium +6 state, like vanadium, iron, those exist in multiple oxidation state. You can able to identify their oxidation state also, as well as their the coordination number by using like this X-ray absorption fine structure spectroscopy. If you see the X-ray absorption near end structure here, that you can see that scattering is a 3 atom scattering here. So there is a blue, green, and red atom. They are interpreting multiple scattering is here. In case of X-jabs, you have a you can see there is a direct interaction, nearest neighbor interaction only. That here the region from the 30 to 40 electron volt here is the band edge here near this pre-edge. So here within the 30 to 40 electron volt in that range region, you will see this X-ray spectroscopy. This way, very small range, and then your the here pre-band edge. Then this is the pre-band edge. Then within the short range, you are getting that this X-ray spectroscopy, and beyond that you have extended 42,000 electron volt past the edge. So you'll be able to see the X-ray spectroscopy. So mainly X-ray is sensitive to the symmetry of the neighboring atom. So since 3 atoms or multiple atoms are there, so you'll be able to get coordination number, valency band structure, you'll be able to get information. But here, in case of X-ray, it's a to nearest neighbor only, you will see the local environment and the distance between the bond length, all those parameters you can able to get from here. So if you see the information wise, what you get from X-rays, like you have you can use this indicator to find bond symmetry, such as tetrahedral, octahedral. Like you have 3 atoms here that they are interfering or vector interfering to each other. So because of this, you will able to get bond symmetry. The tetrahedrally coordinated octahedral, like one atom there, how they are arranged with different atoms, the tetrahedral coordination, you can able to find out. You can able to find out, this make also that indicator for valency of certain system you can found, and can also use in electronic band structure calculation. You can able to, because of multiple scattering involvement, you can also refine that you can get the band structure by using this, X-ray spectroscopy. But if you see the X-rays, they are direct interaction between 2 neighboring atoms, so you'll able to get mainly that information about intermediate local environment surrounding observer and atom. What are the nearest neighbor? So those information you can able to find out by using this. The photoelectron from the green being scattered by the neighboring blue atom. You can see a constant wavefront because of this interference, that you will see that how that wave once that absorption takes place, how this extended absorption, that amplitude keep on changes because of interaction from those interference. You will able to see that mainly that about the intermediate local environment you will able to see. So if you go to interpretation of this X-rays or X-ray spectroscopy, it's quite difficult. And the first you have to see that this is the absorption is occurring like this, that by the X-ray spectroscopy, X-ray spectroscopy, then you have a pre-edge band, you have background like a straight line, you have to subtract from this first. Once you subtract that mu0, that the absorption, that the energy subtraction is mu0e, then after subtraction you will get a post-edge subtraction, you will get this type of spectra. And then isolate the X-ray part. If you isolate this extended part, this part, you will get only that 10 to that below the 40, within the 40 electron volt in that region, like 7.00372. In that region, you will be able to X-rays. If you separate that X-ray part, you will get this X-ray spectra, and then go to derivative of that X-ray spectra, you will get that E0, that maximum of the derivative plot, you will get that E0. Once you get E0, H nu you know, because that is the applied the X-ray photon energy that you apply here. Then E0 you find out from this spectra, you can able to find out the K very easily. And from the K, once you have the K using, these things can be done by, these types of, there are some software available. So with that software, you can able to find out, once the K is calculated, you can find out all the, bond length, oxidation, bond coordination, all those things information you can get. You can see here it's a chromium +6, blue one, and chromium +3. This is octahedrally coordinated, this is tetrahedrally coordinated. You can see how that X-ray spectra, you can getting a sharp in bond edge peak here in case, but in octahedral it's chromium 3 plus, so that peak is absent. So because of this type of dramatic dependence of the oxidation state and coordination chemistry, that you will able to find out different oxidation state by using this X-ray spectroscopy and by using this X-ray. And then you can see another example here. This is calcium chromate CaCrO4, and this is top is chromium metal. From chromium metal to, if you change on this chromium oxide and different composition to finally leads to calcium chromate, you can see here, here there was no, like here you have seen that when you have a tetrahedral coordination, you are getting a peak. Here you can see those when it go to the these are the tetrahedrally coordinated, you can get the peak is there, but in case of chromium metal, this oxidation state 0 or chromium oxide +6, there you are not able to get. So in X-ray spectra of Cr2O3 and chromium metal, where chromium is located at the crystal site, so those information you are able to get by using this, whether it's chromium in which oxidation state, what is the coordination chemistry behind that, whether it's octahedral or tetrahedral symmetry. So those information you can able to get by using this X-ray spectroscopy. Similarly, by X-ray spectroscopy, you can able to get mainly is more complicated to analyze. So that H nu E0 here, K you are getting here. So that K, that is a Fourier transform, that amplitude, how it varies from those parameters we are able to, the complicated equation is there. So you have to Fourier transform the K you will get from by using, once you get E0, you can able to find the K. From the K, you apply Fourier transform to go to real space and then obtain information using various model fitting. So here you can see Fk is the amplitude, phase shift, delta K is the phase shift, and mean free path, how that distances to achieve that path, free path, those things. Once you know coordination number, mean square, digit, all those parameters you can Fk and del K depends on the atomic number. So you can find out that how that adjusts the sensitivity to check the neighboring atom. If a heavy atom or the light atom is neighbor, from that how that exact spectrum is changing. So those information you can able to find out. You can see here, once you have a exact spectroscopy, that you can see that chi-e, that it can be exact analysis first convert to mu e to E that energy chi-e you have to convert. That is equal mu e minus mu 0 e by del mu 0 e, that absorption edge energy, and the background minus that energy of the step. So you'll able to find out that chi, once you know, subsequently from chi versus E data to be converted to chi k, wave vector versus wave vector, how the variation of wave vector with respect to wave vector k you can find out, and then mu E versus, if you flood, you can see how that because of zinc oxide to 2% to manganese to your dysprosium you are adding here. So you will see how the band edge is changing. From this, you can able to find out the distance between those peaks to get that bond length. This is a further you have to go to k square versus k you plot. Then you can find the distance between these two peaks. That will give you the bond distance, coordination number, Diger factor, all those information you can able to get from the exact spectroscopy. So this is quite a little bit complicated, but you can, by using software, you can see this is the ZNO structure here. You can see from this to this, the ZN bond length can be calculated. When you have a manganese, you can see how this peak position is changing from how the bond length is changing. So in a ZNO, you have a 3.8 and whenever 2% now 3.86, so it's how it's changing. So those parameters you can able to find out with the doping and ZN bond length. All those information you can able to find out by using EXAFS spectroscopy. So X-ray absorption fine structure spectroscopy mainly gives two things. One is X-ray near edge, near band edge emission spectroscopy, EXNAS, and X-ray fine structure, extended fine structure, EXAFS. So EXNAS and EXAFS, from there you will able to find out that the oxidation state as well as coordination number, near neighbor atom, symmetry, bond length, it's a bond or as well as bond distance. All those parameters you can able to find out using X-ray absorption spectroscopy. So far we have discussed about X-ray diffraction as well as X-ray absorption spectroscopy. So another spectroscopy that depends on that depends upon X-ray is X-ray fluorescence spectroscopy. So by using X-ray fluorescence spectroscopy, you can able to identify the elemental composition of a crystal of a material. You can able to find out using X-ray fluorescence spectroscopy. So in case of X-ray absorption spectroscopy, your electron or core electron is migrating towards the continuum here. But here in case of X-ray fluorescence spectroscopy, the core electron will go to the higher energy state, field 3D orbital or somewhere that it will go, and then once it go to the excited state, it will bounce back to the ground state. So there time that what are the emission will occur. So the excited core electron will relax back to the ground state by transition of a higher level electron into the core level. That means once the core electron is excited to the excited state, from there it can relax back to the ground state. It will go back to the ground state by a transition of a higher level electron into the core. So core vacant electron. So a higher level electron you can see. Once this electron goes, so the vacant site will be created, unoccupied site it will go, the vacant site will be created. From there, so whatever the 3D electron here, so that is coming here. So you are able to get some, that some sort of, vacant will be created. So whatever the higher energy level electron to the core level migrate, since core level is lower energy position, the excess energy, this is higher energy and this is low energy. Once this high energy comes to here, so it has some extra energy. So that extra energy comes out as a X-ray fluorescent will get. That means that core electron goes out, then what happens that the vacant site will create. This vacant site is filled by the higher energy electron. So since it has low energy, what are the extra energy it has, that is coming out as a X-ray fluorescence. So this energy of the X-ray fluorescent is characteristic of that particular observing material. So that means you can able to find out both qualitative as well as quantitative analysis by using some standards here. To get the exact quantitative analysis, you have to use very good standards. So here if you see, it is instrumentation part. So X-ray source is here. From the X-ray tube, X-ray is coming, falling on the specimen. You have a specimen, and then from here, whatever the X-ray is coming, so those X-rays falling on an analyzing crystal. With respect to XRD, only difference is here that you have an analyzing crystal here. So that analyzing crystal will help you, differentiate the each, K alpha or K beta or K gamma from the different material by energy wise or wavelength wise. That will be, either energy dispersive spectra or a wavelength dispersive. They can identify and by this analyzing crystal and send it to the detector, and you will be able to get this particular elemental analysis. So if it's a nickel, you have nickel K alpha. That means when that n lambda equal 2d sin theta, the Bragg's law satisfies here, so that will be separate out each elements. So as I told, two types of XRF are used. One is energy dispersive X-ray, XRF, energy wavelength dispersive X-ray. So that the energy dispersive, the mostly both are used for the elemental analysis. You no need of any crystalline sample here, but it is also a non-destructive technique and very fast. But you need a very good known material standard to perfect quantification of this. So energy dispersive extra, it's separate, according to the energy or wavelength, it's separated based on the wavelength. So all elements in the samples are excited simultaneously in case of energy dispersive or wavelength dispersive. X-rays are directed to the crystal, which diffract and X-rays of different wavelength according to their diffracts different direction according to their wavelength. So better efficiency will able to get detected without being separated in case of energy dispersive, and whereas in case of better resolution with low efficiency you will get in case of white, in case of wavelength dispersive X-ray fluorescence spectroscopy. So in the both case, you will be able to identify all element here except hydrogen, helium, lithium. It can X-ray fluorescence spectroscopy can detect all elements within a limit of 0.1% except these three elements, hydrogen, helium, and lithium. So here, what will happen? So you have a K and L spectra you will able to get here, like depending upon the element. So those peak you can identify energy wise or wavelength wise, and you will able to get particular element is present or not. This is a milk standard which shows mainly potassium, calcium. Those are present in the milk, so that you can identify using this XRF technique. But here there is some difficulty lies because of interference effect that spectra, like sometimes K and L line of adjacent element they overlaps. That is difficult to subtract environmental interference, like the element like sodium, chlorine emit very weak fluorescence, which can be easily attenuated by the interference with the air or argon atmosphere inside. So because the environmental interference is there, so in addition there is some absorption can be takes place by the absorption of enhancement effect by the matrix interference. So those things takes place. So those that will be interference, or even the isotopic differentiation is also difficult from little bit difficult in this. And for the quantification, you can find out the area under the particular graph, and then the total area divided by the particular elements area. You can find out that this what are the composition present in the material. So whatever so far we discussed about X-ray diffraction techniques. So next 15-20 minutes we'll discuss about the neutron diffraction techniques, like X-ray. Neutron also, as in the first class I have discussed that neutron also diffract, because this neutron is interaction is cross-sectional interaction is very low, because your nucleus is quite small. So because of that, nuclear interaction will be very less. But if those is coming to or closer to the this, if you see the nucleus, the neutron here is quite small, and then because of the electronic shell to the neutron, the nucleus is quite small. So because of that, neutral cross section will be very probability of reaction will be very less. But still, we will be able to get much information from neutron diffraction pattern, like especially for element with as I told, the carbon, hydrogen, like soft element structure, you can able to get from neutron scattering as a neutron diffraction analysis. So if you go to the how to discuss first class about neutron scattering. So nuclear neutron scattering, mainly neutrons scattered in two ways. That one is nuclear scattering, another is magnetic neutron scattering. So being that neutron has a magnetic moment like electron, so there is possibilities of magnetic scattering also. So if you are nuclear neutron scattering, no form factor dependency is here, like structure factor depending that the electron density, that how that X-ray, in case of X-ray, that the scattering intensity depend upon that electron density. Here there is no dependency. And in case of magnetic interaction, if you see the form factor dependence, is there, so it falls faster. In being magnetic interaction, that there is dependence upon the form factor. For nuclear scattering, neutron scattering, it doesn't depend. And it has also temperature dependence in case of magnetic scattering. So neutron with thermal energy less in the range of 10 to 100 milli-electron volt. So they mainly, used in case of this neutron scattering, your neutron diffraction study. And if you see, whatever the scattering intensity you will get, the square of that will depends upon the neutron scattering as well as magnetic scattering, nuclear neutron scattering and magnetic neutron scattering. So summation of both these two, you will get total scattering diffraction or intensity. So if you see the neutron diffraction spectroscopy or neutron diffraction instruments, and you can say it's spectroscopy, it's a neutron diffraction. So you can see here the sample is here, and then you have a reactor source from From the here, the main thing is you have to use the reactor source. From there, the monochromatized beam, the neutron beam which come and fall in the sample. Then it goes to the detector. You have a beam stop here to stop the burning of the detector, and then once it goes like this, it find the detector, can able to find out, can detect those things. So neutron determines the atomic and magnetic structure. Like in case of XRD, you get only the atomic structure of the material. Like you don't get any information or any magnetic structure, whether it's ferromagnetic, antiferromagnetic, how they are, ferromagnetic ordering, atomic ordering, are there in the solids or glasses or in amorphous material. Those information you are not able to get in case of X-ray diffraction technique. But in case of neutron diffraction technique, you will be able to get all those information. It is similar to XRD, but different types of radiation you are using in case you are a neutron, so you get a complementary information. If you compare, see, in case of neutron, so neighbors and isotope can be discriminated. Like you have a cobalt 60 or 59, those difference you can identify by using neutron diffraction technique. But in XRD, you can't go for the isotopic detection. So light element can be detected like carbon, hydrogen, those type of light element you can detect here. It's hard to detect in case of XRD. So magnetic structure, as I told you, the ferromagnetic or antiferromagnetic, those information you can able to get in neutron diffraction. It is a very low absorption, and it's required much time because of nuclear, and the size is quite smaller here. So the electron cloud. So because of that, you need very long time to get a very good spectrum in this pattern. And its availability is very low because you have to associate with a nuclear establishment because nuclear reactor is necessary for the source of the neutron. So if you see neutron diffraction, that that when n lambda equal to 2d sine theta, then these bragg laws are satisfied, you will say that scattering from the nuclei. But in case of magnetic, you will see two types of scattering, whether that there is one is perpendicular, that magnetic moment, that spin orientation is perpendicular to this, another is parallel to this. Oh, sorry, this is parallel, this is perpendicular. So depending upon this parallel or perpendicular scattering, so what you will see, you will able to see that diffraction. But in case of magnetic scattering, only perpendicular one will give you the this contribution to the magnetic scattering. From parallel component will not give any this scattering. So here we use that with the application mainly we use for crystal structure refinement, structural dissociation, or charge order or bond order. Those things you can find out, and spin arrangement in order phase, magnetic factors, all those information you can be able to calculate from the magnetic scattering. So here it's all the scattering is expressed in a term of QF vector Q equal to 4 pi by lambda sine theta, because if you see the X-ray, that neutron source, that from the neutron source, what the diffraction beam is coming out, so that we measure the intensity, and then you will able to get that that diffraction pattern you can generate to find out the structure. So as I discussed in the X-ray diffraction class, so if you see that XRD, you have a structure factor Fn dependent, that scattering factor here. So because of this scattering factor dependent, in case of X-ray, that you can see that there is a scattering factor continuously decreasing here in case of X-ray. So, but in case of neutron, so neutron diffraction, this is the scattering length Bn, that scattering length is dependent. So here this B scattering length is randomly varies. You can see this is hydrogen is quite large and the lithium is small. Then again the sulfur is less and this zirconium is large. But here if you see the hydrogen to cesium, according to increase in the atomic number, how the electron density that it increases. Because of that, the structure factor is increases. As a result, you see that high intense peak in case of XRD, low intensity is stronger and high intensity is very low. That higher 2 theta value, the peak intensity is low. But in neutron diffraction, we get like random, we can get like this type of peak. So that is because of this doesn't have a form factor or structure factor dependence in case of nuclear scattering. But magnetic, there is a dependence. But that is only specific to the magnetic material. But overall, if you see the neutron diffraction structure independent, that independent of that scattering factor, because of that, your peak intensity is very like this. So if you see that neutron diffraction or the advantage that if you take KCl, as you see in case of KCl X-ray diffraction with K and Cl, we have isoelectronic. Because of that 111 peak was missing that we discussed in case of KCl, but in NaCl we used to observe this peak because of Na and Cl, they are not isoelectronic. So here, because of isoelectronic, that destructive interference takes place here between Na and in K and Cl. So it's completely, this peak is completely disappears. But if you go to neutron scattering, so here that is that F K minus FCl is very, very low, that almost 0.06 is negligible or it's almost cancel out. But you see neutron, the FBK, that scattering length of chlorine, potassium to chlorine ratio, you will find out is 0.48. That means it is quite, as you can see, BK and BCl is quite difference, 3.6 and 9.5. So because of this difference, so they will not cancel out that diffraction from K and Cl, the one on plane will not cancel out. We are getting the 1 peak clearly from neutron diffraction pattern, which are absent in case of X-ray diffraction pattern. Another example I have shown here, Ni3Mn. In that case also, that Mn, you can see that Bm minus Mn, superlattice reflection. In case of F, it's the FHK, that all even is possible. Here in X-ray, this is very low, but in neutron, Bni minus and Bm is quite, one is positive, one is negative. This because of this scattering length difference, so you are able, this is quite high. Then what will happen? You will able to see the additional spectrum from neutron scattering in comparison to that of this earlier, that this like KCl and like here you will give additional spectra. Similarly, if you go for that this Ni3Fe, that is an isotope effect, you can see able to see here, that is neutron in cobalt, neutron in 60, and in manganese 60. Here you have a NiFe, that is manganese or something is substitute. You can able to see there is a different substitution of nickel. Substitution here, that because of the difference you can able to see that 0.35 there in neutron in pure nickel, so there is a difference of 0.35. So because of that you will able to get isotopic effect, which are the this Ni3Mn was there here. If Ni3Fe here, you will able to, the isotopic effect can be identified by using this neutron diffraction pattern. You can see here in case of nickel 60 substitution, that what is happening, you are getting this by mistake, this is Mi, this is actually Ni, so Bni and Bni on that 60, so there is a difference minus Bfe. So because of that difference you will able to see the additional diffraction peaks. So if you see the ferromagnetic and antiferromagnetic material, you can see, as I told, that perpendicular only contribute to the diffraction peaks. And so you can see here, if you have a ferromagnetic or antiferromagnetic ordering, that is, the ferromagnetic ordering with respect to magnetic field, all the peaks will be aligned in the direction of magnetic field applied in this direction, all the this alignment in one direction. But in case of antiferromagnetic, they will be oppositely oriented here. So here there is no net magnetization, is 0, but here they will be added off to get net magnetization. Is antiferromagnetic coupling, so that they cancel out each other. So what you can see here, that if you have only magnetic moment perpendicular to Q vector scattering to the contribution, like you have a Q vector, those are perpendicular. So from there you will able to see the ferromagnetic and antiferromagnetic interaction. If you see this example, if you have ferromagnetic material and antiferromagnetic material, that you can see, because the ferromagnetic this and this, or this and this, so there will be a ferromagnetic coupling. So because of this, the peak intensity, but in case of initially it may be this, so because of ferromagnetic, so there will be enhancement. So this enhancement is mainly due to ferromagnetic ordering. But in case of antiferromagnetic, you can see there is a additional peak, some of the additional peaks, those things you will be able to see, because one is A lattice here and B lattice going down direction. So you'll be able to see the both these peaks, you can see ferromagnetic, these peaks are there, these peaks are there, these three peaks are there in both cases. If it is a antiferromagnetic, that peak is added up. With antiferromagnetic, you can see additional peaks. This peak intensity is same. So those, because of this, you will able to both and nuclear as well magnetic interaction there. So you'll able to get both chemical cell as well as magnetic interference. Both you will able to get. So here is an example that nickel manganese oxide antiferromagnetic. You can see here, even X-ray diffraction pattern, you are not getting a peak here. In case of neutron, if you go low temperature, this 111 peak, that is antiferromagnetic interaction, that peak at low angle, very low temperature, and able to see those type of peak. So main drawback is neutron's diffraction, as I told, its fluxes is very low because experimental take too large time, and you need a large reactor type or spallation source facility to get this type of structure. And neutron observing element like cadmium, gadolinium, samarium, boron, they will interfere in these studies. And today's lecture, so mainly what we discuss is about three XRD technique that we discuss. One is single crystal XRD technique. So that will tell you the 3D electron density mapping. From there, the atomic arrangement you can able to get, and grazing angle XRD that you can use for depth profiling and thin film analysis, and synchrotron XRD that can use also better resolution, you can able to get even at low percentage detection, 0.1% detection limit you can able to get, and then high temperature, high pressure studies you can do. Even high temperature studies can be also possible with this conventional XRD, but better information will get using synchrotron radiation. And X-ray absorption spectroscopy, that is that fine structure we discuss, exness and exapse, that gives neighboring atom structure, coordination number, valency band structure, and oxidation state. All those information you can able to get. This especially coordination number is this mainly this technique gives coordination number that can able to get. On X-ray, by X-ray fluorescence spectroscopy, you can also identify that composition analysis, element analysis you can able to do. And from neutron diffraction pattern, you can see both atomic and magnetic structure, which is complementary to the X-ray information. What are some information which you could not get in X-ray, you'll able to get neutron diffraction. It gives the information about light element like carbon, hydrogen, those type of things you can able to get. So we'll conclude today's lecture here. So next class we'll discuss about scattering technique, that is small angle neutron scattering and small angle X-ray scattering. Okay.